Okay, this is the second part of our chemical bonding lecture, this one on chapter 9, which is going to cover molecular geometries and then the theory of bonding and why different bonds look the way they are, interbond distance and strengths and things like that. So knowing the shape of a molecule is pretty important, right? Because that really dictates its reactivity and how many bonds it's going to form and what it's going to look like and things like that. And so if you know the number of bonding and non-bonding electron pairs, you can pretty easily figure out or at least predict what the shape of the molecule is going to look like. And some of the things we're going to be talking about is you have like a linear molecule like this, right? But at the same time, sometimes you have, this guy has a bent shape. They still both have 3 different atoms bound together, but now this one's bent. Or sometimes you have this guy here with 4, it makes this trigonal planar shape, but this guy has 4 and it's a trigonal pyramidal shape. Or you could end up being a T shape. So we're going to be talking about what it is that causes this differences in shape. So basically the electron pairs, whether they're bonding or non-bonding, are going to repel each other. Okay? If you assume that those electron pairs are going to want to place themselves as far away from each other as possible because of those repulsions, then you can predict the shape of the molecule. And the best way to do this is to look at electron domains. And so you can refer to electron pairs as a specific electron domain. They can be bound electrons or they could be non-binding electrons, like I just said. Even if it's a double bond, they are still on the same side of the central atom, so they're going to count as one electron domain. So if we're looking at this molecule here, how many electron domains do you have? That's an electron domain. This is one. This still counts as one, and there's another one. So this one would have 4 electron domains. And so this leads us to what we call VSEPR, valence shell electron pair repulsion theory. And basically tells us, like I was saying, that the best arrangement is the one that minimizes the repulsions between electron domains. And so there's lots of these tables in your book that sort of help you figure out what these molecules are going to look like. And so if we're just looking at electron domain geometries, this is what you kind of look at. So if we had something that had an S and a P orbital, it's going to have this linear shape, right? If you had S and a P, you'd have a trigonal planar shape, or you could have a tetrahedral shape. So basically all I have to do is figure out how many electron domains there are in the Lewis structure, and that can help you figure out what that the geometry would be. So if we're looking at NH3, this is how we would draw it. 1, 2, 3, these guys are another electron domain, so you have 4 electron domains. And so it would have a tetrahedral electron domain geometry. But this electron domain geometry is not always the shape of the molecule. So really the molecular geometry is different from the electron domain geometry in that it's defined by the positions only of the atoms of the molecules and not the non-bonding pairs. So the way to figure this guy out, same idea, you're still going to take your chemical formula, you're going to draw your Lewis structure, and now we're going to figure out we can figure out our electron domains. Okay, but then you can figure out the molecular geometry by only looking at how many non-bonding electron domains there are. So there's 1 non-bonding, 3 bonding, and so this is going to be slightly different. This guy is not tetrahedral, this is trigonal pyramidal. So then basically this means within each electron domain, there could be more than one, there probably is more than one electron geometry. So if we're looking at this guy, you would have a tetrahedral electron domain geometry, but you could remove this guy, and now this no longer counts, right? So if we're looking at just the molecular, now it's trigonal pyramidal, and if you were to take away another one, you'd be looking at more of a bent molecule. So in the linear domain, just one molecular geometry, linear, obviously, right? If you only have 2 electron domains, this is what you're going to this is what you're going to get. And obviously, if you only have two atoms in a molecule, it's always going to be linear because that's the only way you can do it. So if you had two bonding domains, no non-bonding pairs, this is what you're going to get, right? Because there's no non-binding pairs to affect the shape of this molecule. If we're looking at something that's trigonal planar, now there's two different molecular geometries that you could get, right? So we have three electron domains here. You could have trigonal planar if all the electron domains are binding. So this guy here would be a trigonal planar, but now if one of these guys is no longer participating in a bond, it's not linear because this guy is pushing these atoms a little bit farther away. So now you end up getting a bent geometry. And this is because, like I said, these non-bonding pairs are physically larger than the bonding pairs, so they have greater repulsions. So they're going to decrease the bond angles. So if you're looking at something like what we were just comparing, if you have something that's trigonal planar, right, this guy is going to be exerting some force, pushing these guys down. This bond angle is 107 degrees. Now if we had two, they're pushing together and creating this bent molecule at 104.5. So no matter, you can see, and this guy's 109.5. This is the greatest one because there's no non-bonding pairs to sort of mess with it a little bit. When you have multiple bonds, double and triple bonds, these guys put an even greater electron density on one side of that atom, so they're also going to affect your bond angles. And so you can see here, you have a lot of electrons concentrated right here. So instead of being equal all the way around, this is a greater bond angle. These electrons are forcing these chlorines away from them a little bit, so decreasing that angle. Now if we look at the tetrahedral electron domain, there's three different molecular geometries we could look at. So again, 4 electron domains. This would be a tetrahedral electron domain geometry. So you could have all 4 of them bound together, and so then in this case the molecular geometry would be same as the electron domain geometry, and you still end up with tetrahedral. If you had one non-bonding pair, it's going to look like this guy here, which would be trigonal pyramidal, and then if it's 2 and 2, you're going to end up with the bent. If you're looking at something that's trigonal bipyramidal electron domains, so now we have 1, 2, 3, 4, 5. Basically, there are 2 distinct possibilities of which you could have for this geometry. You could have equatorial electrons or equatorial atoms or axial atoms. So this would be the axial position. This would be the equatorial position. And you can actually get lower energy conformations by having the non-bonding pairs in the equatorial space rather than the axial space. And so this is going to have a greater effect on the geometries in this way. So you'd be more likely, if you had just the non-bonding pair, for it to be here than for it to be in the axial space. So you're going to end up with this molecule looking here. Sometimes it's called the seesaw molecule. You can imagine, this would be the seat, and this would be the pivot point right here. And so if we're looking at this guy, again, we have 5 electron domains. If all of them are bound, you're going to have the trigonal bipyramidal. If you have one non-bonding domain, that's when you end up with a seesaw, like I just said. If you took away 2, again, they'd rather come from the equatorial position, so now you're going to get a T-shaped molecule. And then if you have 3 unbound and now only 2 bound, now you're still rather going to come from the equatorial instead of the axial. So now you're going to end up with a linear molecule because these guys, the repulsions are all going to be spread out evenly. And so this is going to end up with a linear shaped molecule. If we're looking at an octahedral electron domain, now again, 6 electron domains, these guys have basically equivalent positions, and so there are 3 different geometries you could get. Obviously, you could have octahedral if they're all connected. If you have one domain that's not bound, so you have 5 bonding, 1 none, you're going to end up with a square pyramidal. So in this case, they're going to be happier by taking those electrons from the axial position as opposed to the equatorial position. And so then if you take away another one, again, it's going to come from the axial, so you end up with a square planar molecule. So this is all great when you're talking about something with one central atom, but when we have these big, large molecules, how do you do it? Well, it doesn't really make sense to talk about molecular geometry for something that's really, really big. So usually you're going to talk more about the electron geometry around one particular atom. So if we're looking at this particular one, you have the electron domain would be tetrahedral, and there's no unbound pair. So again, that's going to be, the molecular geometry would be the same. This guy here would have a trigonal planar electron domain geometry, same thing for the molecular geometry. But then if we're looking at this one here, electron domains would be tetrahedral, two unbound pairs, but the actual molecular geometry around that one would be considered bent. In Chapter 8, we talked about bond dipoles and how to determine if a certain molecule were polar, but just because a molecule has polar bonds does not mean the whole molecule is necessarily polar, right? So if you look at this guy here, we obviously have, like, this would be considered a polar bond, right? Because the oxygen is going to be pulling the electrons a little closer to it, and there's going to be pulling electrons a little closer to it, and you see that down here. But really overall, because everything is balanced, this overall molecule has no dipole moment because basically they cancel each other out. They're equally and oppositely directed bond dipoles. So this molecule as a whole is not polar, even though it's made up of polar bonds. And so basically, just like we just said, by adding the individual bond dipoles, you can figure out the overall dipole moment for a particular molecule. This example, on the other hand, does have an overall dipole moment because these guys are not equal but opposite. They're both pulling in the same way, in fact. So you can see there's definitely a much greater charge over on this end. So you have the partially negative side over here and the partially positive side over here. So this is a polar molecule in this case. So when the bond dipoles are equal in magnitude and opposite from each other, they cancel each other out. So this guy here, right, obviously there's nothing to cancel out, so it's polar. This one, though, would be considered nonpolar because it's equal all the way around and everything cancels each other out. Right? Same thing with this guy. There's three of them, they're all pulling equally. This guy would be considered polar, though. This is more of a bent or a T shape. So this guy is not canceling out equally but oppositely. And then this guy, even though it's tetrahedral and you have four different directions, is not pulling. This guy, this chlorine, is pulling a lot harder than the hydrogens are pulling. So this guy would be polar. So you have to think of the molecule as a whole. And so this leads us a little bit to the overlap in the bonding of these electrons. So we think of these covalent bonds as sharing the electrons. And like we said, though, this is really just an overlap of the area where the electrons are, and this is basically where we find them. So this idea only works when the whole orbital of the atoms overlap. So really that's what we're thinking about, is we're thinking about the overlapping of the orbitals, because the orbitals are where you're most likely to find the electrons. And so if you recall the previous video, we talked about electron density and finding greater electron density between the molecules. And so this increased overlap brings the electrons and the nuclei closer together, but at the same time, it's also decreasing the electron-to-electron repulsion. But if you get too close, then all of a sudden the internuclear repulsions greatly increase, and so they're going to start pushing each other away. And all this means is that for every bond, there's basically a sweet spot, right? So over here, the potential energy is decreasing because of the bond overlap, right? So right now there's a balance between the attractive forces of the nucleus and the repulsive forces of the electrons. But here, this axis is the distance from the nucleus. As we start to get closer and closer to the nucleus, now you're getting a lot more energy repelling them apart. So over here, they're pushing them closer together. Here, they're pushing them apart, and here's that sweet spot. So this is where that distance is going to lie. The next thing I want to talk about is hybrid orbitals. And this is something we've actually really been working with, though you probably didn't necessarily know it. So it's kind of weird. But if we think about beryllium, right? So if you picture the periodic table, which I know you can all bring up in your head, and you think about where beryllium is, we've been talking about beryllium as have, being 1s2, it would be 2s2. We would think, okay, it's got 2s electrons, it's got 2 valence electrons, and so it's going to be able to form 2 bonds. And that's what we've been working on. That's the assumption we've been working on, and everything's been fine. But when we look at our electron diagram, we see that all the electrons are paired. And if they're paired, then they're not as interested in forming bonds. So what the heck's going on? According to this diagram, there's no free electron that can just go and bind with something else. But we know that beryllium is perfectly able to form bonds with 2 other atoms. So how do we resolve this? If that atom were to absorb just a small amount of energy and it could excite one of these electrons, one of these 2s electrons, up to the 2p level, we've seen that happening. Okay, hey, great, now we've got 2 unpaired electrons. Now we could form 2 bonds. But that doesn't really work out quite right. I mean, it seems to make sense, but the problem is now you're dealing with an s orbital and a p orbital. And those guys are not the same size and shape. So this would not produce a linear molecule. But if you look at something like beryllium difluoride, that is a linear molecule. Experimentally, we see linear molecules. So obviously, this isn't really the best explanation. But if you were to mix the s and the p orbitals together, you get 2 degenerate orbitals that are hybrids of the 2. So we would call this an sp hybrid orbital. And basically, you'd be taking your s and you adding your p. Remember, the p looks like this guy here, and they hybridize, and you end up with these 2 guys here. And then when you look at them together, it really looks more like the standard p orbital, except it's a little bit bigger. And so these guys then would align themselves 180 degrees from each other, and then this would produce the geometry that is consistent with experimental results, produces this experimental linear geometry. So you have there's the sp hybrid orbitals, and then the fluorine's 2p atomic orbital. And so we would draw the electron diagram like this. Now, instead of having a 1s and a 2s, we've taken one of our p electrons, so now instead of the 3 boxes, there's only 2, and we bumped it down there. And so we've got sp2. And so this orbital has more energy than the 1s, but less energy than the 2p. And so we can do this with lots of different types of atoms. And so if we look at boron, this guy is actually going to hybridize one of the s's and then 2 of the p's. And when these guys all come together, you end up with this sp2 hybrid orbital. So you can just think of this as, right, we're combining 3 things. So sp2, there's 2 of them, 3 things combined together. And this is going to give us this trigonal planar arrangement. And again, this is consistent with what we see experimentally. With carbon, again, we've always think of carbon as being able to form 4 bonds, but if we were to look at the electron orbital diagram, that wouldn't necessarily be true. It would only be 2. But if we take 3 of the p orbitals and hybridize it with one of the s orbitals, now we get all these guys put together is going to form this tetrahedral shape. You get the sp3 hybridization. So again, sp3, 4 things happening. 1, 2, 3, 4. And the easy way to figure this out basically is to look at the Lewis dot diagram and see how many electron domains you have. If you have 4 electron domains, then you're going to have sp3 hybridization because you've got 4 things going on. And so this plays a major role in the valence bond theory as it applies to bonding, right? So there's 2 different ways that orbitals could overlap to form bonds between atoms. And so this is going to explain a little bit about the distance between bonds and strength between bonds and things like that. So we're looking at sigma bonds. This is something you would see in a single bond. So here we have this, just 2 p orbitals overlapping here in between the 2 atoms. So it's a head-to-head overlap. It's a cylindrical symmetry of electron density around the internuclear axis. So here's your cylinder right there. If we're looking at a pi bond, though, these guys are going above and below that internuclear axis. And so this case, you're getting a side-to-side overlap. The side of this p balloon is overlapping with the side of this p balloon. And obviously, these guys aren't as close, right? It's not spreading out as much. So these guys are going to end up being a lot closer together for this overlap to happen. So if we're looking at single bonds, again, single bonds are always going to be a sigma bond because this is the greatest overlap, so this is going to be the strongest bond. It's going to be the most favorable electron energy. In a multiple bond, though, so such as this guy down here, one of the bonds is going to be a sigma bond, and then the rest of the bonds in that multiple bond pair are going to be pi bonds. So in this case, you have a single sigma bond and a single pi bond. If we're looking at this guy, the triple bond, now still have one sigma, but now you're going to have two pi bonds. So just to look at these guys a little bit more closely, so we're looking at something like formaldehyde. So this is something that has a double bond between the C's. And so if we were to look at the electron domain geometry, there's 3 electron domains around each of the carbons because one of them is a double bond. And so you have an sp2 orbital on the carbon. So that's what you have here, your sp2. That's the purple. And you still have one of your p's remains unhybridized. So that's still just a straight up p. And now the unhybridized p orbitals are going to overlap in the pi fashion. So there's your unhybridized p overlapping. There's your sp2 overlapping. So there's your one sigma bond, and this is your one. Both those together are your one. Is your single pi bond. If we're looking at a triple bond, so something like acetylene is going to look like this. You've got one sigma, 2 pi's. So we still have 2 sp orbitals are going to form that sigma bond. Okay, so this is going to form an sp orbital. We have 2 electron domains, 1, 2, so it's sp hybridization. There's your sp is going to form one bond, but now you still have 2 p orbitals that remain unhybridized, and those guys are going to be free to form the pi bonds. So there's a pi bond. There's another set of pi bonds on each one. And so altogether, you've got one sigma. Here's a pi right here, and then here's another pi perpendicular to that. So finally, to wrap this up and kind of bring things home, we've talked a little bit already about delocalized electrons. We've talked about resonance structures. And so when you think of something like the nitrate ion here, we know that we can draw resonance structures for this because you can put the double bond here, you can put the double bond here, you put the double bond here, and they're basically all equal. And so we've talked about all that before. But reality with that, what we're saying is that each of these atoms has the p orbital, and then the p orbitals in all 3 of the oxygens are able to overlap with the p orbital of the central nitrogen. And so really, if this is what it's looking like. And so these guys would be considered delocalized. Right here it's localized, they're stuck here. But now really what's going on is those electrons are kind of basically free to be anywhere in there, because again it's electron probability. So this is what it looks like in reality, and we call that delocalized. So the pi electrons are not localized between the nitrogen, and they're delocalized throughout the ion. And similarly, we talked about like a benzene ring, and this is going to have 6 pi bonds and a p orbital on each of the carbon atoms. So it's going to look like this, right? So here's your sp2s, and then here's your pi's, or your p orbitals. And so these guys are all going to form the sigmas, and then your leftover p orbitals are going to be forming your double bonds. Okay? And so they're not localized, they're delocalized, so there's going to be an even distribution of those pi bonds in the benzene ring. So just like we talked about when you draw this, if you were to draw this, you draw your hexagon and you draw a circle in it to signify a delocalized resonance structure. This is part of the reason why, because this is what's really happening. Those bonds are all free to, or those electrons are free to be anywhere in there. They're delocalized. And that is it for our chemical bonding lecture.